All right, so we can flip those. It doesn't really matter. Or you can just go with this and solve it from there. When you're going to need this is if you know the hypotenuse and one leg. You can just plug it in that formula. Otherwise, you could plug it in this formula and do the algebra from there. We've all mostly at least seen the Pythagorean theorem, right? Whether you remember it or how to use it, except for Peter. Peter's just stuck in shaking his head mode. Yeah, go on. We've heard of it, right? How many times have we proven it that it's true? All the time? Each time?
Yes.
Yeah.
Physics.
Oh, in physics, yeah.
Maybe.
I'm going to show you one proof. One proof of it. So it's not like a paragraph proof. It's not a two-column proof. It's more of a visual proof in understanding areas. All right. Just looking at those two drawings that we got A, B, A, B, A, B. Do we agree that the area would be the same on both of those? Maybe. Well, wouldn't the area of this one be A plus B times A plus B, right? And the area of this one would be A plus B times A plus B. Do we agree that that would be the areas? So they have the exact same areas. I'm just going to draw something so we can show the area in a different manner. So what I'm going to do on this first drawing is I'm going to connect these dots going straight across. Then all I'm going to do is I'm going to find the area of each of these little boxes I created. So that top left one, the area of that one would be, well, area of a box or a square or anything is length times width. So this one's going to be A times A, which is just A squared. My other box here, I'm going to use the A first because we could look at it as B times A, but I'm going to go call it A times B. So the area of this box here is A times B. The area of that lower left box is also A times B. It's the same exact size. So that one's also A times B. Let me just call that AB like I did in the other one. That last box we didn't name yet is B squared. So our area, which we could call A plus B times A plus B, well, we can also write that as just adding up all those areas from the inside, which would be A squared plus, well, I have two of those ABs, so it'd be 2AB plus B squared. And if you FOIL out that binomial times a binomial, you'd see that that's true also. So we all agree that this is the area, right? If anyone doesn't buy that, you're not going to buy the proof. Yes? Oh, yeah. Is it 255? Okay. All right, but we all agree that, I thought you were going to say, no, I don't agree. But we have to buy into the fact that this is the area. All right, that's the area of it. Because we're going to find the area of the other one, but we're going to use a different method. We are going to connect the dots at angles. I am going to name, I'm going to name these lines that I just created. I'm going to call them all C because they're all the exact same length. Each of those lines is the exact same length. So what's the area of that inside box I just created?
C squared.
Anyone? Shout it out.
C squared.
C squared.
Did you say B squared?
We said C squared. So the area of that is C squared. All right, if we notice, we also created 4 triangles. I'm going to highlight one of them. So that's one of our triangles. I created 4 triangles, right? I got this guy, that guy, that guy, that guy, and they're all the exact same size triangle. So now all I have to do is I have to remember how do I find the area of a triangle? How do I find the area of a triangle?
1/2 base times height.
1/2 times base times height. So area of a triangle is 1/2 base. I don't know if I have enough room. Base times height. Just for the sake of everything coming out even, I'm going to call this my base, because you can call whatever on the bottom is your base. So that means my height of my triangle would be B. So the area of this particular triangle, that's going to be 1/2. My base is A. My height is B. How many of those did I say I had?
4.
I have 4 of them. I got 4 of those guys. All right, so if I want to put the area of this triangle, or this square, my area is going to equal all the things that were added up. So I'm going to have that C squared plus the area of the 4 triangles, which would be 4 times 1/2 A times B. So it's just, I'm adding 1/2 AB, 1/2 AB, 1/2 AB, 1/2 AB, and adding together. That's 4 times. Well, in more simple terms, this is just C squared plus 4 times 1/2 is 2 AB. Yes?
That would be that's why it's the same for A squared plus B squared equals C squared.
C squared, when we put them next to each other, yep. Because we know that this area is the exact same as this area, right? So I can set this area equals to this. Doesn't matter how I wrote it, they all have to come out to the same number. If this came out to 64, this would have to come out to 64. Because it's the same square, it's just a different way to come about to the area. So what we're going to do is we're going to set those two things equally to each other. So the first way I found area was A squared plus 2AB plus B squared. That has to be equal to the second way I found the area, which was C squared plus 2AB. But if I was trying to solve it, I would subtract 2AB from both sides. Because I'm allowed to do that as long as I do it to both sides. That would cancel, that would cancel. And we're left with A squared plus B squared equals C squared. No long two-column proof necessary. It was all basic arithmetic and a little bit of geometry mixed in there. We got A squared plus B squared equals C squared. And it's true. You don't have to take it on faith. And in fact, there's multiple ways to solve this. Like Nicholas, I think you were saying that you solved it many different ways. Or you did it a few times.
Well, we used it in physics class.
Oh, okay. You used it in physics class. All right. Because there's multiple ways to prove. They've proven it. It's a very, very famous theorem, so it's been proven many, many, many times. All right. Paragraph style, 2-column note style, different ones. There's lots of cool ones out there, but this is one way. Just so you know for a fact it is true. I'm not going to put that on a test or anything, but just so you know it is true. All right. How do we use Pythagorean theorem? So we're going to find x by using the Pythagorean theorem. We're not going to use the Pythagorean triples, so we're going to cross that out for right now. We're going to get into that later. We'll get into that once we're good and ready to do that. All right. So the first thing I'm always going to note is which one's my hypotenuse. My hypotenuse is always the long one, or I can look for the one that's across from that right angle. So that my hypotenuse is 5. So for this particular one of our legs is x, so I'm going to go x squared. Plus the other leg squared has to equal my hypotenuse squared. I can't do anything with my x, so I'm going to leave that as x squared. Well, 3 squared is just 9. 5 squared is 25. Solving for x, I would subtract 9 from both sides. And I'd come up with x squared equals 16. Do I care what x squared equals? Is that my end goal, to know what x squared equals? No, I want to know what x equals. How do I get rid of x? How do I get rid of that square that's attached to it? I already asked Mary. Yep. I'm just going to take the square root of it. Am I allowed to take the square root of one side? Probably not. Remember, what you do to one side, you have to do to the other side. So if I take the square root of one side, I have to take the square root of the other side. Now, square roots and square, they're inverses of each other, so they cancel each other out. So if I'm doing x squared and I square root it, basically our square root and our square cancel out. I'm just left with x equals the square root of 16, which is 4. Don't forget this. In algebra, you learn when you took the square root, you have positive and negative answers, right? That holds true in algebra. It just doesn't hold true in our class, all right? Because we don't have lengths that are negative. So we're just going to go straight to the positive answer. But keep in the back of your brain knowing that when I get to algebra, I need to, like when you get to algebra 2, reacquaint yourself with the fact that when I take the square root, it's positive and negative. Don't go back to Mr. Piggin says that was positive. All right? That only works for my class, geometry. Is it only positive? All right. So we have x equals 4. On our next one, our hypotenuse this time is x. So we're going to have one leg. I'll call it 4 squared plus 6 squared has to equal x squared. Well, 4 squared is 16. Plus 6 squared is 36. Equals x squared. 16 plus 36, that must equal 52. And then we'll use Mary's trick of square root of both sides. And let me go up here. Hint, hint, we probably still have more work. I give that answer on my test. Does Mr. Paving give me full points for that?
No.
Well, you're not taking the test, so you probably get full. Would your teacher give you full points for that?
No, because it's not in the simplest form.
It's not in the simplest form. Who knows what perfect square goes into 52? What perfect square goes into 52? Lauren? 4 does. And how many times does 4 go into it?
13.
So we could rewrite this as square root of 4 times 13, which is going to be x equals 2 times the square root of 13. Now you get your full points. Don't lose a point because you're too lazy just on your... Remember, I told you to use calculators, right? Don't be too lazy to use a calculator and go, 52, it's a bigger number. I don't want to check to see if 4 goes into it or 9 goes into it. That's too much work. All right, don't lose points because of that. All right, our next one, we have 4 square root of 6 is one side, x is another side, and 12 is our hypotenuse. Remember, right across from there gives us our hypotenuse. So we're going to have 4 square root of 6 squared plus x squared equals 12 squared. Well, when I square this, actually, let me do this on the next slide really quick, because I know I ran out of room in the other class, so I moved it over here. There we go. Now we got more room. All right, when I square this, what I do in my head is I do the 4 times the 4 first. So I kind of distribute this square. So I do the 4 times the 4, which is 16, times the square root of 6 times the square root of 6, which is 6, plus x squared equals 144. And what's 16 times 6? I bet it has something to do with 60 and adding 36 to it. That's my guess. That has something to do with 60 and adding 36 to it. Yeah.
With 60?
96.
Wait,
I was just doing a little mental
I thought
math.
you meant 16.
No. Yeah, I did 16 times 6, so I was saying, because 6 times 10 is going to be 60, and then you add the 36 onto it. It's just some quick mental math. Plus x squared equals 144. I'm going to subtract that 96 from both sides. Cancel that guy out. We're going to have x squared equals 48. I take the square root of both sides. And I have x equals square root of 48. And I am too lazy to check that, right? No, we're not too lazy to check that. What goes into 48? There? 16 absolutely goes good. Would it have been okay if you picked 4 and then you had to do 4 again? Yeah, it's fine. All right, but Mary saw that 16 went into it evenly, so we can say that's the square root of 16 times 3. Square root of 16 is 4 times the square root of 3, and we are done now. Because I guarantee there's not a perfect square that goes into 3. Minus 1, but 1 doesn't help us. All right, D is kind of one of those that if you're on a test, you get stuck and then you quit. Just do what you know how to do, all right, and see what shakes out of the tree from there. So I see I have an 8, I have an x, I have an x plus 2, and so at first I'm like, I need 2 numbers to solve it. Well, let's not quit. Let's just see what happens if I do the exact same thing. So if I do a leg, which is 8 squared plus x squared equals the hypotenuse squared. And just a quick reminder that x plus 2 squared is x plus 2 times x plus 2. Well, hey, I can keep going. Right? This shouldn't stop us. It shouldn't be like, well, there's nothing I can do. Because we know 8 squared is 64 plus x squared. Now, however you do this, if you do FOIL, however you want to do this, we're going to distribute this x plus 2 into this x plus 2. What I always did when I taught algebra is I said, well, we'd have x times x, x times 2. What was that? 2 times x. And 2 times 2. So I never ever taught FOIL or any one of those methods. I just taught distributing.
I hate foil.
Just look at it as distributing. X has to be distributed to both things. 2 has to be distributed to both things. You do that drawing and you never get it wrong. All right, so we have x times x, which gives us x squared. I have x times 2, which is 2x. But I also have 2 times x, which is another 2x. So that's 4 x's. And then we have 2 times 2, which gives me 4. The first thing I want to do is I want to get rid of these x squared, because that could be foiling, but thankfully, or not foiling, factoring. But they cancel out, so we're left with 64 equals 4x plus 4. Hey, this looks like something I can actually solve. I subtract 4 from both sides. I come up with 60 equals 4x. And someone tell me what x equals. Anyone to shout it out. 15. 15, and we are done. If I asked for the particular side, you'd say that this side is 15 and this one is 17. I didn't really specify what I wanted here, but I'm just going to write that in there.